It's a little rough. I saw you guys in your attempt, though, when I was grading it. P.S. When I was grading, I took off points for things just left totally blank. I took off points for directions not really being written. Some of you got used to having a couple words in TAs just saying, yeah, that's good. Anyway, what else did I take off points for? Not finishing. It was pretty much formatting and then not trying stuff. Now, here's a quick heads up. If I'm able to see every homework assignment, did I ever expect perfection as far as you guys getting everything on every assignment? Did I ever expect that? No, I didn't. So how can you, in your pictures, how can you show me if you really tried to understand a section of homework with certain directions and like you really tried it and you're really stuck? Should it just be like a whole section that's blank? Think it like a teacher. What is a teacher going to think if a whole section is just blank? That you were lazy. Okay, so how do you show me in pictures that you really tried it and you're stuck? Yeah, maybe. You can do I'm really stuck. Or couldn't you even, like, I don't know, with a colored pen, because nothing's going to be in colored pen, have like a highlighter or something that you just put a question mark on? And you've written the directions, you've written the problem. Nothing should be totally blank ever, right? You've written, or at least summarized the directions, you've written the problem, because that's what we do in here. And then, I mean, if you're able to try something and it's just not matching up, it's not the answer in the back of the book, you've tried an odd, and that's like the even, and it's not even close. Like, then just put a big old question mark so that I can see, okay, they wrote it down, they got all the way up to the very end, and now they're stuck. Like, then I can tell at least you tried something. Does that make sense, kind of? Okay, and or you can even, like, be specific and be like, directions, question mark, like you don't even know what it's asking. It can be like, this term, I don't know, something like orthogonal. You can be like, orthogonal, question mark, and I'm like, oh, they have no idea what that word means. Like, you can't even give me a hint before we get to class about what you're stuck on. But also, when you get to class, you can be like, psh, my hand's going up because right here I have a question and I know what I don't even know what it was asking me right there, right? Like, it's super easy for you to access your questions now. Anyway, you guys all sent me pictures of this assignment, so you should all be able to grade it right now unless it's not with you in class. Number 2 and number 4, we're just asking you to get a good picture. You don't have to have it exactly like this, but the long story short, 0 to 2 pi in radian mode would have been great, or 0 to 360 in degree would have also been fine. This one, a zoom standard, would have been okay, but you should have been a little more zoomed in. This one, zoom standard, would not have been okay. You needed to be a little bit zoomed out. Did you have to write down necessarily everything? You could have done X-mins, X-maxes. If you graded the odd in the back of the book, you would have seen what kind of answer they were looking for. Does that kind of make sense, guys? Okay. But on your paper right now, shouldn't you have had sketches of graphs and not just answers? Remember writing directions and problems? Okay, sorry. Number 6 was the next one, right? Yeah. Okay, so what's going on? I mean, at first you're getting a picture, right? And then you're trying to figure out the initial point with... did they give you a time interval on number 6? Did my book actually load? No, well, or I don't have. Okay, that's great. I do have, because I signed in. Anyway, that's awkward. Okay, let's forget that for right now. It's not working. Letter A, was there a time interval for letter A? Or is it just like all real numbers? Yes. Okay, so for the time interval, you were able to kind of plug in and hopefully figure out the initial point that way, terminal point. Oh, so that makes sense. Okay, so first of all, the parameterized curve, you're first just getting it into Cartesian or rectangular equations. So you're first just eliminating the parameter and getting y equal x squared. But the problem is that it's not the entire x squared. So the parameterized curve, even though x squared is the entire path, the path that this is on is only going to be this portion of the parabola, which they then go ahead and say the left half of the parabola defined by that. So they did it in an awkward way. I would have probably just done it simply by saying y equals x squared for x less than or equal to, because it hits 0, 0, right? That's what I would have done. So you're restricting it to be the only portion that's actually being. However, what did they do that was actually pretty creative in that it doesn't need a stated domain? How'd they just get the left-hand side? Yeah, they did it implicitly. Because they were saying, like, hey, a parabola has two branches, has two halves. And so if I was to solve for x, like an inverse sort of, if I was to solve for x plus or minus square root, it's really just the negative square root of y. So it's awkward because it's implicit. It's actually pretty ingenious in that this would go ahead and just have positive y's. Well, that's always what the parabola has, but it would only be the negative x's that would be included as opposed to the positive x's. So that was super cool and all, but technically this would be just as valid in the sense of it's the whole parabola but only the left-hand side. Does that make sense? So the whole parameterized curve is just them being snazzy, being like, hey, what's the path this thing is actually on? Oh, the path is x squared, but only the left-hand side of x squared. So it's kind of discounting, remember, it's eliminating all of the parameter, all of the t, all of the timing. Okay, the next even was number 14, but just because that one was nasty, were there any of the odds around there that you guys didn't understand with the whole parameterized curve thing? Yeah, Naomi? Number 9. Number 9, the easiest way to parameterize this one, to eliminate the parameter, and consider just the function would have been to use that cool trick of getting cosine alone, sine alone, cosine squared plus sine squared is 1. So x squared plus y squared is 1. So we know it's a circle with a radius of 1 by eliminating the parameter, using those trig properties. We know it's a circle. But when you guys were graphing, you should have just seen that it was only the upper part of that circle. And so, once again, you could have just stated that x squared plus y squared is 1, comma, for what, y greater than or equal to 0. That would have worked. But thinking about when you solve for x plus or minus square root, when you solve for y plus or minus square root, thinking about whenever you have plus or minus square roots, it talks about different portions of the graph. You could have just solved for y and only kept the positive square root part, which should have been the top. So there were a couple of different ways of doing that. But Naomi, does that make sense, kind of? Yeah. And then if you were looking at, what were the original parametric equations? That's going to help us actually a little bit. What's x equal? Cosine. Just cosine. And then y is sine? Okay. So if x is cosine and y is sine, if you're just looking at this, x will never be bigger than 1, lower than negative 1. Neither will y. How come? Because cosine and sine are restricted, right, guys? Not even restricted. They're just kind of defined to be in between negative 1 and, oh my, between negative 1 and 1. So we already knew that all the x's and y's had to be in between 1 and negative 1. And as far as the initial point, terminal point, what was the interval, Naomi? T is?
Greater than or less than 0. Or greater than or equal to. And then pi.
So then to get the initial terminal, just plug in 0 and then plug in pi, and you can tell where it began, where it ended. But there we go. Anything else in that whole parameterized section where they were asking you to graph it and show the orientation? We're okay? Okay. Number 14 was the next even, yeah? I wouldn't say the parameterized curve. I would say eliminate the parameter. Yeah, and I probably wouldn't ask for domain restrictions or any of that jazz either. It's a little weird, I know. And it's parametric. Calculus's take on parametric and polar for an intro. So it's a little bit deeper than we're probably used to. But the nice thing is, for those of you guys that are like, I'm hating this beginning, chapter 2 is limits. Like, it's limits. Like, maybe we'll see it a little differently, but it's limits. Chapter 3 goes into basic derivatives. Chapter 4, and motion. Basic derivatives and motion. Chapter 4, that's when chain rule comes up. Like, we're going to go fast, but it's not going to be weird. Just a couple things along the way is going to be different, and so we're just trying to get used to seeing it different ways. Does that make sense? For those of you that are like, my life, rip, right? Okay. Sorry, number 14. Did you guys get the sine and cosine alone? And then square and plug into your formula? And if you guys were to follow it, it's just going to keep on following the exact same. So they because it just keeps on going around and around and around as you plug in. Did they give you a time interval on that one, or was it just all real numbers? Oh, but they did 0 to 2 pi. Okay, so it does the entire curve. Got it, got it. Next one, I have no idea because I wasn't paying attention. Sorry. 38. Okay, so then number 20. It's a weird direction. It's coming this 2, terminal point 40. Y equals the square root of 4 minus x. And then they did what I did. They just said, oh, hey, it's for x greater than 0. Greater than or equal to 0. Because if x is greater than or equal to 0, then y is positive. And it's naturally restricted. So some of you might have said something to the effect of greater than or equal to 0, less than or equal to 4, if you were to think about it now, like how you're restricting it. But you don't need to say less than or equal to 4, because the function itself is already, remember, naturally defined to be less than or equal to 4. So you just need the greater than or equal to 0 to cut it off. Good? We don't like those? Okay. Okay. I really wish I had a picture. Sorry, Mrs. Christensen is getting to where hopefully I can get my ebook again. It just doesn't give me access, and it's kind of silly. Section 1.4. I really liked these ones, 29 to 32, but it is tricky. 29 to 32 gives you no, it's not even open. Oh my goodness. I got having too much fun getting pre-cal all saved and closed. Okay. Let me do this. This is the cheater way I figured out last year. Ready? Nope. Why? Hold on. Un momento, por favor. What made number 29 through 32 difficult? I totally agree, it was. Okay. So in 29 and 32, they gave you a graph. And for that graph, it's a weird V thingamabob that's like backwards. And where's the vertex at? 3, negative 1-ish? Does that look right? So it goes down to like 3, negative 1-ish, and then it goes down like that. Okay. And then what are my parametric equations? X equals? And what's my y? And do they give me any sort of other restrictions? T is in between negative 5 and 5? How many of you guys got stuck at some point, or at least this slowed you down on 29 to 32? Huh, okay. Some of you, come on, be confident, be real. When you were trying to think about each of the different quadrants, you had to think about what would make the x's positive, y is positive, x is negative, y is positive, x is negative, y is negative, x is positive, y is negative, right? Basically, because that's what defines quadrant 1, quadrant 2, quadrant 3, quadrant 4 as far as distinctly from each other. So when, in number 29, they just asked for, wasn't just each of the different quadrants? For quadrant 1, quadrant 2, quadrant 3, and quadrant 4. You could look at your function and say, okay, first of all, what would make y positive? Well, y is going to be greater than 0 for t greater than 1, right? And then y is going to be negative when t is less than 1. What about t equal to 1? Well, it's on the axis, right? Okay, so when is x going to be positive? When t is less than 3 or not equal to, because that would be on the axis, greater than negative 3. Because wouldn't negative 3 also be a positive 3? Ah. So then when is x going to be negative? When t is greater than 3 or t is less than. Does that make sense? Because I needed this little absolute value, positive or negative numbers, to be less than 3, which means inside the magnitude's negative 3 to 3. Then outside that, well, that's going to go ahead negative 4, negative 5, negative 6. Oh, I can't go beyond. So now I just need to take my inequality and say, okay, so I'm going from, if you want to think about it, you guys thought sign charts were only supposed to be used for increasing, decreasing. Couldn't you think of signs of x and y? And you have these little markers of negative 3 and 3 and 1. And couldn't you just think through and say, okay, hold on, x is going to be positive for any of these and negative elsewhere, right? Y is going to be positive anywhere greater than 1 and negative elsewhere. Third quadrant. Hold on. Fourth quadrant. First quadrant. Second quadrant. Dun, 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 dun. Inequalities. Is that me being creative with my calculus skills? Yes. But does it apply? It can. Has nothing to do with derivatives, but that's pretty snazzy. Thinking about the domains and thinking about positives and negatives and quadrants, and then saying sign chart, hey, look, I can see it all. But you could have also played with like the different numbers and tried to think of, okay, so from negative 5 to negative 3, x is negative, but sign chart makes it so much nicer. Oh, hold on. Because 5 and negative 5 wasn't a natural cutting off. So these ones are zeros. Let's see. This would be a 0 of x, right? The 3 and negative 3 would be zeros of x, which would be y-intercepts. Not y, yeah, y-intercepts. So those aren't allowed to be on or in like a quadrant. And then 1 is the x-intercept. But 5 and negative 5 were just out in the middle of nowhere, so they needed to be included. Does that make sense? Cool. It's kind of like when we're talking about calculus. Aren't there some times intervals where critical points are some of the numbers, and so they aren't included for like increasing and decreasing? But then at other times, some of the points are just like endpoints where they cut it awkwardly, but they do need to be included in intervals. Similar to that. You guys are like, we're not in calculus yet. Okay, anyway. Go team. That was 29 through 32, all of them, right? Cool. So let's go back to, what was our next one? 38, 34? 38. Thanks. True. Okay, any questions? Is that the end of the evens? I think so, right? Evens or odds? We're okay? Okay, so quick reminder on homework. When you guys take pictures and do Google Classroom, I'm just seeing that you attempted it. Make sure your questions are clear as far as, you don't have to write paragraphs. That's not the point. I don't want to add to your time or to the, I just want to help keep you accountable and make it so that when you come to class, you're like, oh, I'm ready, right? I already thought through, and these are the ones I'm stuck on. Except for the evens that you grade and maybe get wrong. You might have a few additional questions you didn't know until you come in and grade it. But on test day, we're still turning in our homework spirals, but the TA and or me will just be looking for, I'm hoping I get another TA, but we'll see. We'll be looking for, did you finish up what you didn't have ready by the pictures? Did you finish it all up? Did you have it all graded and corrected and hopefully questions answered and ready to go by the test? Does that make sense? Oh, because the whole quiz. Let's just figure out whether or not we're having the quiz tomorrow. Sound good? Let's go do polar. We need to figure that out before we talk about the other stuff. But yeah, it would count because it's like the end of this section as we know it, pre-cal review. We ended yesterday with, oh guys, look. Check out the notes. Why am I encouraged? There's 2 examples and then the homework. So we finished all the notes yesterday. So I'm thinking that we don't have to go and be behind. But let's check out how the examples go. And let's see, for those of you guys that started homework, any questions you have. And then theoretically, like, I don't think this will take me more than 5 minutes, but it depends on how many questions you have. But we might be able to go ahead and just go to homework. But anyway, yesterday we talked about conversions. If we need to make parametric equations, we're literally plugging into, and you might want to do like a little highlighting. We're not making this a forever card right this second, but we might. We will eventually, actually, second semester. This will be in a forever card. How you can take an r equals f of theta and make an x of theta, y of theta. Make an x equals, make a y equals, make it parametrically defined. If you were using the parameterized, it would be see, it just works differently. That's so awkward. Parametrically. Anyway, so we're going to use this one, and this one's going to be like literally, it's going to seem like you're pulling out of nowhere, but you're not. You're plugging it into these formulas right here. X equals r cosine, y equals r sine. You're actually plugging into that. But this one is the more natural conversion where you're going from a parametrically defined to eliminate, a polar equation. We're not eliminating anything. A polar equation to a function using, how did we do this yesterday? How did we do secant? It was awkward. It was weird. How did we go from having theta to not having theta? Plugged what in? Yes, but was it from the list of 4 formulas that we had talked about? No. So what did we consider instead? The entire triangle. Good. So even though these formulas are good and these are the most commonly used, are there a lot more formulas in a right triangle having to do with cosecant and cotangent and tangent and secant? Yes. Just to keep in mind, you can have all of those as formulas. What did I do at the very end? I said r is equal to the square root of x squared plus y squared. And I said done. Dun, 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 dun. Could I have gone further? Sure, but I didn't want to. Okay, what if we were to go from polar to parametric? Not polar to function, not polar to rectangular, but polar to parametric. And let's say I was to give you something like r is equal to 1 plus, let's just do cosine of theta. Okay, so this is the polar curve, r equals f of theta. If you guys haven't yet, calculators, polar mode, r equals, you're going to have it looking like r's, right? And when you hit the little variable button, what's going to show up? T for parametric, theta for polar. Because in your mode, function comes first, x, parametric comes second, t, polar comes next, theta, sequence comes next, n. That's fun. Okay. Polar to parametric. Somehow I need to get an x equals and a y equals. Wait. What formula do we have for x equals with polar? It's one of the main 4. Yep. So before I ever get to the final, I just need to say who is r cosine theta. And then for y, do the exact same thing, because what's the formula for y? R to go from polar to parametric, it's weird. We're literally plugging into formulas. We're literally saying take the r cosine, take the r sine theta, and put in r. Put in r. Simplify if you want. Parametric, we literally just put them into x will always be r cosine theta. Y will always be r sine theta. That's always how we can parametrically define any polar curve. So I don't know. I mean, I guess you could simplify it to be what? Cosine theta plus cosine squared, but is that really that much simpler? Maybe. This one could be sine theta plus sine theta cosine theta. That's okay. I took these 2 formulas that are, does it make sense, my basic 4? And I just said, whose r this time? Right? It's so backwards because we're so used to just like playing around with all these relationships and getting this variable to go away, and that's not like this. This is literally just plugging in and saying who's our. But it's weird because our brains aren't ready for it, and then we just get confused. Does anybody else not see it? We're taking these two formulas last time. And once they define who R is, we don't mind the theta. We actually want the theta. We don't have to get t's, because remember, we're getting x of theta, y of theta. Yes, there'll be t's in our calculator, but theta is fine. It's a third variable. And we're just saying who is R to plug in. This guy this time, cool. Who is R? This guy this time, cool. And then we just simplify. Then we have x equal, y equal with a third variable, theta. So where does that bring us? Graphing. It's the very last skill. Graphing is the very last skill. How do you graph with a calculator and without a calculator? With a calculator and without a calculator. As you guys are getting at graphing, using a table or memorizing. Ooh, memorizing. But first with a calculator, just to make sure that we can use it. 2 minus 2 cosine of theta. Everybody's here today, right? Yeah. You guys see a table up there, right? Okay. So with that table that's up there, don't we normally, like if we were doing tables, wouldn't we, I don't know, go plugging in stuff like -2, -1, 1, 2, a 0? Why am I not? Definitely not. Most definitely. I have trig functions. Unit circle stuff. I wouldn't start at pi over 2. I'd probably start at, what do you guys think? Yep, I would start at 0. And then what would I go to? Did you not say 0? Why? Someone else said 0. Someone said 0, didn't they? I could have sworn you said 0. It's that low voice. Don't do pi over 4. Why wouldn't I do pi over 4? Doesn't pi over 4 or cosine have root 2 over 2 as part of its value? Give me a decimal equivalent for root 2. Give me a decimal. Multiply by 2. 2.8. How about 2 minus 2.8? All right, so long story short, maybe we shouldn't be using pi over 4. Why would I say maybe 0, pi over 3, pi over 2, 2 pi over 3, and pi? Why am I awkwardly skipping pi over 6 and pi over 4? Because they have radicals in them, whereas the other ones don't. Does that make sense? You guys start making me a table, and I want you filling out. Start making me a table and fill it out. I would say skip the radical ones, and let's see if we can get a good enough picture without. I know, I have it in my calculator, but I don't want us to do that quite yet. I would go all the way to 2 pi, but maybe pi is enough. You can pause at pi and put the points in and see if you can figure out what the picture is. Yeah. Yeah. Exactly. But the problem is, Ariane, you are going to have to fill in the blanks because it would be nicer to have those decimals in there. No. But it might be nice because you're going to have to go from one point to another and you might not see exactly the connection. Does that make sense? Okay, I get to come and have fun now? You guys got a head start? How am I cheating? This is pre-cal. That's true. I agree with that. Longer since you guys had pre-cal, most of you. Cosine of 0 is 1, right? 1/2? 0? Negative 1/2? Good. And then negative 1? Ooh. Okay, hold on. We're just doing trig right now. We're just doing trig. It's okay. Cosine of 0 is 1 times 2, 2 minus. I'm going to pause and graph. Because you guys want to do as little as possible. Understandably so, to some extent. So we're seeing if we can figure out a picture. Why am I going out 4 and no more? Ooh. Why is it the max? What's the highest cosine can go? 1, which gets me to 0. What's the lowest cosine can go? Negative 1, which gets me to 4. Just going between 0 and 4. Pi over 3, rotate. Pi over 2. 2 pi over 3, rotate. Now some of you are like, I don't know what that is. Polar always rotates with how you graph. And if we were to do some of those radical-y ones, with the square root of 3 and the square root of 2, using those decimal equivalents that maybe you memorized from Mrs. Leon or Mr. Che. P.S. They both taught chem. Maybe there's a pattern as to why they have random radicals. Or they're just cooler than I am. You would have been able to fill in RN for pi over 6 pi. You would have been able to fill in a couple of these, so it would have been more natural. But if you kind of get the feel for how polar works, maybe it's not that crazy. And certain symmetries. Symmetries. It's a limaçon. A limaçon with a cusp. Mm-hmm. Yes, there's a point right there. That's 3. And if I had done another pi over 3, I would have had another 3, wherever he is.
So, like,
Then a 2.
this could be like a calculated question.
Could be. Except, here's a dealio. I could have either given you harder problems on the quiz and let you use your calculator, or easier problems on the quiz and not let you use your calculator. I chose with the easier problems. With the no calculator. I chose the easier problems. Now here's the problem with the view. It's a little bit iffy as to whether or not you can see the cusp. I'm not so sure I can see it. Because the problem is the pixels have to go out. If you had zoomed in, I bet you could see the cusp a little bit better. Oops. Well, there you go. There he is. There's a little cusp. Why is he called a limaçon, a snail? It doesn't make sense, right? Because sometimes if the cosine, or I should say if the term with the cosine does not have added or subtracted, as long as these two don't match, if this guy right here were to be bigger, then if he was to be bigger, then it would be possible for this to go negative, and if the r went negative, it can sometimes trace in on itself, something like that, and then all of a sudden we call him a snail, because then plus the word limaçon means snail, and you can give him little eyes, and you can give him a little there he is, he's a snail. But this guy did not go in on itself because the r's never went negative. Since the r's never went negative, there was no, this is just the shell, not the snail. The poor little guy, he left. Anyway. Did we need to keep going? You could have. And if you had kept going, you would have been able to keep on tracing. But sometimes with symmetry, you can kind of just figure out and keep going from there. So let's see if you guys can figure out this one. The numbers do not match. And it's a sine. But Aryan already helped you out because he was like, well, wait a minute. If we use pi over 3s with cosine because it's a nice number, with sines, you would use pi over 6. Let's see how many angles you need in order to try to get a picture. Then you can check with your calculator. I'll give you a head start because I'm nice. P.S. I'm like collecting forever cards and calculators and all. If you guys lose stuff, just come ask me if it's valuable because I'm just keeping it so that other hands don't steal them. My turn, can I play? If it was up to some of you guys, I would never do anything. Never answer. Why am I only going out 4? The maximum r I can get is at pi over 2, which is 4. Good, because the highest sine can go is 1, and the lowest sine can go is -1, right? So is it possible for this r to go negative? And the answer is yes. Huh. Sine of 0 is 0. 1/2. Yeah, 2.5. Good. Pi over 2 is 5 pi over 6 is, because sine is positive in the second quadrant. And then, now here's the struggle. This one maybe you should have kept going because sine hasn't even gotten negative yet, right? Because now sine goes negative. So now I have -1/2, which is going to be -0.5. Is that right? And then I'm going to have -1, which is going to be -2. And 11 pi over 6 again. Maybe some of you guys realize the symmetry. So if that's true, didn't actually need to draw these, but just for sake of argument. Okay, 0, 1. Got it. Pi over 6 and 2.5. And then 4. And then 2.5-ish. And then 1. So far you're like, yay, okay, I get it, it's spinning. But what's the struggle right about there? That should have been more out. I apologize. That's okay. Now all of a sudden, what's it do? Negative? What's it doing? It's becoming a snail. There's our Lee missile with an inner loop. It went in on itself. Technically, you guys could have seen that this one also, it does have a cusp in a sense, because this can't equal 0. It would be when sine is, what, -1/3, which is a legal value of sine. So it would have zeros, but it doesn't just have zeros. It doesn't just hit. It keeps going inwards, and then it comes back out, and then it keeps going from there. Anyway, graphing by hand. You have to know unit circle. My advice is to choose nice little values as far as when sine is 1/2, when cosine is 1/2, instead of the weird radical-y things, especially if we're doing by hand. Technically, you can memorize some stuff with polar, and when we get there in chapter 11, I'll pull up this big chart where it's like, hey, anytime an equation looks like this, it'll be a limacon, with a loop, without a loop. Anytime it looks like this, it'll be one of those lemniscate, like infinity sign. Anytime it looks like this, it's going to be a circle. And anytime it looks like this, like, there are things you can memorize. But don't you have to memorize a lot for calculus anyway? If you could just do this every time, you can, as long as you get a feel for how polar is always rotating, maybe you won't have to memorize that huge old table of like 20 different possible graphs and their variations and how they occur. Kiddos, homework is homework number 2. There he is. If you guys want to write him down in your homework spiral, he's up there and he's ready to go. Those of you guys that have started, did we get stuck anywhere? I'm not sure we started, huh? Okay, let me just add this down. Let me read what the different directions are of the problems that I gave you. Plot the points. Plot the points in polar and give or convert to rectangular. Plot the points in rectangular and give or convert to polar. Find the appropriate window to get the curve or the sketch in your calculator. Convert from polar to rectangular. Oh, that one's fun. I only gave you one of those two. That one's find the slope at the curve. Oh, no. That's a different assignment. I was going to say, I was like, there's no way I did that yet. That's like derivative. Okay, good. That's second semester. So then we stop. We stop with number... Okay, so stop at number 39, and then we go over to, like a variation on a distance formula, playing with polar points. And that's it. Oh, true, false. But we definitely answered that one in class, like multiple times. Okay. It's not as bad as it looks because the first chunk is plotting points, plotting polar points, making them rectangular, plotting rectangular points and making them polar. And then you're doing some conversions along the way. So here's the dealio. Tomorrow, beginning of class, let's grade homework. Let's go over homework questions. The quiz is 5 questions, which includes graphing a parametric and showing the orientation, converting, eliminating the parameter, I should put it that way. Eliminating the parameter, graphing polar points / equations, and converting polar to rectangular or otherwise. So it's really just graphing and converting the whole time. I mean, you throw a limited parameter in there, but the whole thing is just graphing and converting. So we'll take it at the end of class tomorrow because it's like the summer quiz as far as just one piece of paper, like one side, but I've spread everything out to give you room and graphs and tables and whatnot, and I think it's 4 or 5 questions. But we'll go over homework questions first. Sound good? So it's graphing with tables, parametric, polar, converting parametric to rectangular or vice versa, thinking like eliminate the parameter. And then it's converting polar to rectangular or vice versa points, converting polar to rectangular or vice versa equations. Yeah. Then we'll see how homework goes. Yeah, Hannah.
I have a question on the previous example.
Yes.
No.
Oh, this one? Got it.
How it turns in on itself, log 197 pi over 6 and
Oh, because remember negative radii, so here's 7 pi over 6, but instead of going towards that angle, negative means you go backwards. So I just went 180 away, which was towards pi over 6. You go backwards from the origin. That was 1, so I went backwards a half. Does that make sense? And then 3 pi over 2, I went backwards 2. Then 11 pi over 6, I went backwards that little half again. Yeah, it's going like backwards in on itself. Aryan? I can figure out a way to put a bonus on there. I'm not sure it'll be that easy, but it won't be anything that's too crazy as far as initial term. Like, it won't go into that. I'll have more fun with it. Yeah, I'll get a bonus on there. All right, anything else? Questions? Yeah. Yes. Why don't you just take your stuff with you because we have 15 seconds. Go for it. Are you sure you can get a head start out in the hallway? It's not a bad thing.